with something different compared to what was done yesterday. And then we'll move on to any questions or queries that you have. Okay, so we'll start with this question. So you're given two permutations, and so the question asks what is their composition, right? So we'll probably just recap what is a permutation and how do you compose two permutations before answering this question. So just to recap, a permutation is, so let's say permutation on a finite set. So usually if the set has cardinality n, we just take it as 1 to n. So on a set S, which is 1 to, let's say up to n. So permutation is a bijective function from S to S. Right? So let's just take a small example. So we'll take our n to be, let's say 5. So we have the set 1, 2, 3, 4, 5. So any function which is bijective, and just to recall what is a bijection? A bijection is a 1, 1 and onto function. Bijection is a 1, 1 and onto function. So maybe I'll write a few functions from S to S and you can tell me which of these is a permutation and which of it is not. So let's just look at one example. So maybe I'll just denote it pictorially. It will be easier to visualize. And once we understand what it is, we will move on to see how do you represent a permutation and how do you, different ways of representing a permutations and how do you work with it. So let's say 1 goes to 1, 2 goes to 3. This is the first example. Second one. So and just one more. Okay, so you can start typing in the chat box if 1 and 2 are permutations while I write the third one. Right. So out of 1, 2, 3, which of them are permutations and which are not? Can somebody reply?
Number 3 is the permutation. 1 and 2 are not permutations.
Yes, you can. Yeah. Okay. So the third one is a permutation, as some of you have already guessed, and these are not permutations. So this and this are not permutations because you can see that they are not bijective. 3 and 4 are going to the same element, which means they are not 1, 1, or they are not on 2 because 2 doesn't have a pre-image. Either way you look at it, they are not permutations. And this is a permutation. Okay. So with this, we'll look at how do you represent permutations. Right? So let's take the third permutation that we had. So what is this? See, usually this is how we represent it. Okay. So okay, let's first write it in the function form. So if we call this f, so what is this? F of 1 is 3, f of 2 is 2, f of 3 is 1, f of 4 is 4, f of 5 is 5. So this is the function that we are looking at. So this is a bijection, hence a permutation. So usually we just represent it in a much simpler way. So what we do is we write two rows of numbers. So the first row is just 1, 2, 3, 4, 5. So whatever you see here in the domain, that is what we are writing in the first row. And second row is what is the image of the element in the top row under this bijection F. So let's say a common way of representing a permutation. So, right. So what is the image of 1? 3. So we put 3 below 1. This means f of 1 is 3. Okay. Now what is f of 2? It is 2. So we put 2 below 2. And what is f of 3? 1. F of 4 is 4. And f of 5 is 5. Right. So this is how we usually will represent a permutation. And let's do one example where we do the other way. So we have a representation and we're trying to get the function. So let's say G is this permutation. So we have 1, 2, 3, 4, 5. Right? So what does it mean? G is the function which takes 1 to 3, 2 to 2, 3 to 1, 4 to 5 and 5 to 4. So G of 1 is 3, G of 2 is 2, and G of 5 is 4. So the fact that G is a permutation or it's a bijective function, it is captured by looking at the second row, right? Every number appears only once in the second row. That's what is capturing the fact that it's a bijective function. So are there any questions so far?
No.
If you have a question, yes, you can answer. Krishna ji, you can ask your question.
Ma'am, can you also explain the process of writing the permutation as a product of two cycles?
Yeah, we'll come to that. Is there any questions? But how will ensure it is onto? See, one thing is if each number appears only once, then it has to be onto, right? Because we are in a finite set. So you have 5 numbers and everything, and you have 5 places. So if each number occurs once, then all the numbers have to come, right? There are 5 students and you have 5 benches. So if you make the 5 students sit in the 5 benches, all the benches will be occupied. So it has to be onto. Otherwise, you can manually check 1, 2, 3, 4, 5. All of them have appeared. I hope that answers your question. But in the codomain, there may be no. When we say a permutation, we have a finite set S. So if you look at it, the definition is you have a finite set S and we're looking at bijections from S to S. So it's not bijections from some, yeah. Okay. Okay, so now let's look at how to compose it and the question that Malvika asked, how do you write it as a product of two cycles? But before that, let's understand what is a cycle. So let's take this permutation. 1, 2, 3, 4, 5. Okay. So what is this? If you look at it, you have 1 and the image of 1 is 2. So let me just use an arrow to denote it. So 1 goes to 2, right? You have 2 and the image of 2 is 3. So you have 2 goes to 3. And then 3 image is 4. So we'll write it as 4. 4 is going to 5 and 5 is going to 1. So if you see, it looks cyclic. So this is what we call as a cycle. So if you have something like this, where under the function, an element is going to something else, that is going to something, and then it's forming a complete circle. So instead of writing such a long notation, we will just simplify it. We will write it as, so expressing a cycle. So instead of writing this first row, second row, we can just write it as 1, 2, 3, 4, 5. What does this mean? 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes to 1. Right? So this is what it means. Now, suppose we have something else. Let's say 1, 2, 3, 4, 5, and we have this. So let's see what is happening here. We have 1 is going to 2, 2 is going to 3, and 3 is going to 1. So it's a smaller cycle, and the other two elements, they are going to themselves. So 4, it's going to itself, 5, it's going to itself. So how do we write this? We say 1, 2, 3, right? This is to accommodate this cycle. This means 1 goes to 2, 2 goes to 3, 3 goes to 1. 4, it's going to itself. So it's a single cycle. And 5 is also going to itself. So for notational sake, if it is a single, we don't even put it. We just remove this. So whatever is not put, it is understood that it is going to itself. So G, we can represent it as 1, 2, 3. Just the cycle 1, 2, 3. And one last example. So let's say we have 1, 2, 3, 4, 5. Okay. So can you try to get this permutation into cycle type? Can any of you, can you try typing it in the chat box? How do you write this in cycle type?
One, two, three, 4, 5. First cycle is 1, 2, 3, and second is 4, 5.
Yes. So what is happening? You have 1. 1 is going to 2. Image of 1 is 2. Image of 2 is 3. 3 is going to 1. So this is giving you one cycle. And you have 4, which is going to 5, and 5 is going to 4. Right? So you can try out with some more examples, bigger numbers, take n equal to 7 and take a permutation on the set of 7 elements and so on. But you'll see that any permutation, you can write it like this, as product of cycles. Okay, so now let us look at, let's say, 2, 1, 3, 4, 5. Okay, so this, if you write it, 1 goes to 2, 2 goes to 1, and everything else is fixed. So if you write it in cycle type, this is basically 1, 2, right? So the length of the cycle, when we say length of the cycle, we mean the number of terms which come in the cycle. So this is cycle of length 2. This is cycle of length 3. So if it is a cycle of length 2, we call it a transposition. So
If the length of the cycle is 0, then can it be length of the cycle is 0?
0, you mean there is nothing, but that is not, sorry?
But it is a permutation, no? 1 goes to
So
1,
when you say
2
0,
goes to
you
2,
mean
3 goes to 3, 4 goes to 4, and 5 goes to 5. Then it is a permutation. But
yes,
there is
yes.
no cycle. But there is no cycle at all, no?
Yeah, so you can write this as product of, you just, all are one cycles. See, what happened is here also there are cycles of length 1. So there is 3, 4, 5. We're just suppressing it for notational purposes.
No, what I mean,
Mm-hmm.
if the length of the cycle is 0, if the length of the cycle is 0, then in that case, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, and 5 goes to 5. It is a permutation.
Yes, sir,
But
it is a
length,
permutation.
but length is 0, no? Length of the cycle,
Length is not 0, it is 1.
it is 1.
See, this
Okay.
is a cycle, right? Just 1. 1 goes to itself. So
Okay,
what
okay.
is the length of this? 1, right?
Okay, okay. Okay, I got it.
Any more questions?
No.
Okay. No questions in chat box. Okay. So, now we will see what do we mean by composition of two permutations. How do you or multiply two permutations? See, we
Ma'am,
have,
can you please excuse me, ma'am?
yes,
Can you
yes.
please show how we are representing every cycle as a product of two cycles?
Yes, yes, I'll come to that. First, we should know what is the
Okay.
product of cycles, what is product of
Okay.
permutations, right? Yeah.
Okay,
So I'll
ma'am.
just explain what it means for product of permutations and then we'll come to how to represent it.
Okay, ma'am.
Okay. So we have a permutation F and we have a permutation G. So okay. So what do we mean by product? So you know they are functions from S to S, right? So what is F? It is a function from S to S. And G is also a function from S to S. So we know what we mean, what it means to take composition of functions. So F composite G, we know what this is. So this is how we'll define product of, it's just composition of functions. So keep this aside. Yeah. So what we want is Fg at any element is basically f of g of that element, right? So let's look at it. What happens? Let's look at one image of 1. So what does g do to 1? It sends 1 to 2. So it is f of g of 1, which is 2. Now what is f of 2? It is 3. So we'll do the computation for all the other elements also. So fg at 2 is f of g of 2. So g of 2 is 1 and f of 1 is 1. So this is 1. So fg at 3 is f of g at 3 which is G sends 3 to 4 and F sends 4 to 5. So this is 5. G of 4 is 2 and F of G of 5 is 4. So now let us see what we have got. This F composite with G. FG is this permutation. So 1, 2, 3, 4, 5. So 1 has gone to 3, 2 has gone to 1, 3 has gone to 5, 4 has gone to 2, 5 has gone to 4. So I've just written it out for sake of clarity. You can, let's just do one example without writing it into so many details. 2, 4, 5, 1, 2, 3, 4, 5. Okay. So we'll just try to orally do it so that you get a hang of how to do it, and it will be much faster. So let's say this is F and this is G. So we want to compute FG, right? So we have 1, 2, 3, 4, 5. We just want to see the image under F composite G. So you take one, look at, see, when we do the composition, we have Fg of 1 is F of G of 1. So first thing we are acting on 1 is G. We are looking at G of 1 and then looking at what F does to it. So if we want to directly do it with a, using the notations. So first thing we'll look at is the rightmost permutation. So just keep this in mind. So we look at where 1 goes to 4, and in this 4 goes to 4. So 1 goes to 4. So here 2 goes to 1. So we'll look at F now. 1 goes to 1. So 2 goes to 1. So now 3. Here 3 goes to 3. And then under F, 3 goes to 2. So the final result is this. Now you want to see the image of 4. So look at the image of 4 here, 2. You go here, look at where 2 goes to, and that is your final answer. And finally, 5. Okay, I hope, is this clear?
Yes, ma'am.
Okay, some of you have given the answer, FG. That's nice. Okay. So let's rewrite this in terms of cycles. So what is this? Again, let's try to do it without using, without writing out every step. So we have 1. Sorry? Yeah.
1, 4, 1, 4, 3, 2, 1.
Yeah. So 1 is
1, 4, 3, 2. 1, 4, 3, 2.
yeah. So here 2 goes to 3 and 3 goes to 2. So that is the permutation, and 4 is going to itself, 5 is going to itself, 1 is going to itself. So if this is F into G, so if you look at G, look at 1, 1 goes to 4. So we put 4. Now you look at 4. Where does 4 go to? 2. Now you look at 2. 2 goes back to 1. So we can close this cycle. Then you take something that doesn't appear in this cycle, so which is 3 and 5. So again, as I said, for notational purposes, every cycle of length 1, we just ignore it. We don't need to write it. You can ignore all of these. So this is equal to 1, 4, 3, 2. Okay, I hope it's clear till now. Any questions? Earlier FG is different. Which FG? You mean this one? That was a different example. There F and G were also different. This is, let's say, example 2. Is that okay? Yeah. So this was, let's call it example 1. Okay. If there are no more questions, now we'll come to the question about writing everything as product of transposition. So, okay. So the one important result is every permutation can be written as a product of transpositions, right? So just to recall, what is transpositions? Cycles of length 2. Sometimes they are also just simply called 2 cycles. So how do we write a permutation as a product of transpositions? So what have we seen here? Every permutation, we saw how we can write it as a product of cycles, right? So if we have a cycle and if that cycle can be written as product of transpositions, then our job is done, right? So let me write what I'm trying to say. So what we'll do is every permutation can be written as a product of cycles. And so what we'll do is we'll take every cycle and we'll show that that can be written as product of 2 cycles. So the second thing is any product of transpositions. Okay. So first we'll see how do we write a cycle. So let's look at 1, 2, 3, 4, 5. This cycle, right? So I'll just write the permutation. So F is equal to this, which is 1, 2, 3, 4, 5. Okay, let me number the example. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. So this is what it is. Okay. How do we write? See, if you want to naively think about it, this is like, let's say you have some 5 boxes. 1, 2, 3, 4, 5. And you have 5 objects. So this permutation is kind of telling you which object to send to which box, right? So if you think of the top one as boxes, and let's say the down one as, the objects. So it's saying, okay, you send the object number 2 to the box 1. So naively saying, what you want to do is take these objects and put it in these boxes. Originally, let's say they are in some position. Let's say they are like this. Somebody just placed it like this. Now you want to reshuffle it so that it becomes this permutation that you have, and you only have 2 hands. So at a time you can only move 2 objects into 2 different boxes. So that's what we're saying when we say that it can be written as a product of transpositions, right? So at a time you're moving 2 objects, but doing that multiple times you can reach whatever permutation you want. So that's the idea of writing every permutation as a product of transpositions. So last step once, no, I'll tell you explicitly how to write it. I was just giving an analogy as to why the thought of writing it as a product of transpositions. Okay, so what we'll do is we'll first move, see, what do we want? We want 5 to go to 1, right? So let's just first perform that operation. We'll send 1 to 5, sorry, 5 to 1. Or if, okay. Now, but if we just leave it like this, what is happening? 1 is going to 5. We don't want that. So what we'll do is, we'll again send 1 to some other place, and we'll keep doing this process. So given a cycle, this is how you write it as product of transpositions. Let's check it. I know I just said it. So let's actually multiply and check. Okay, so this is what we claim. Let's see if it actually works. So you can actually try, shifting the boxes and see that this is how you would actually try to do it. So let's see. So you look at the left hand side, we have already written it as a permutation. Now the right hand side, what is 1, 5? It is 1, 2, 3, 4, 5, 5, 1, and everything else. Okay, is it clear what I'm trying to do? So the claim is that once you have a cycle, you can write it as a product of transposition this way. So what did we do? If you just want it as a, as a process, we took 1 with 5, then 1, 4, 1, 3, and 1, 2. Right? So we're just trying to check that this actually works. Okay. So what we're trying to do is compute the right hand side of the equality. So, so 1, 5 is 1, 2, 3, 4, 5, 5, 2, 3, 4, 1. This is 4. This is 1, 2, 3, 4, 5. So I'm just doing whatever we did previously, converting the cycle notation to this, actually explicitly writing out the function. And this is 1, 2, 3, 4, 5. So if you compute the, you just take the product of all of these, we will see, okay, let's just do it for one element. So what is happening? Let's see where 1 goes to. 1 goes to 2. Then you come here, 2 goes to 2. Come here, 2 goes to 2. 2 goes to 2. So after performing all these operations, eventually our 1 is going to 2. Next, you look at 2. So we always start from the rightmost function. So you look at the image of 2. 2 goes to 1. Come here, see where 1 goes to. 1 goes to 3. Come here, 3 goes to 3, and 3 goes to 3. So your end result is 2 goes to 3. So we can complete it for all the other elements also. So is there any questions in this? Okay. So let's just look at a general permutation. So let's say is okay, maybe taking a bigger number would help, because now let us take S is equal to the set, a permutation on the set of more than 5 elements. Let's take 7 elements. So we'll take the permutation F is 6, 7. Okay, so what is this? How do we
Ma'am,
write?
can you please explain the verb example again?
Which one? The one I did previously? Okay,
Yes.
explain example 3 one more time. Okay. Okay, see, what are we trying to do here? We are taking a cycle and we're trying to write it as a product of two cycles, right? So that's what we're trying to do here in this example. Writing a cycle as a product of transpositions or two cycles. Is this part clear that this is what we are trying to do?
Yes, ma'am.
Okay. So we took an example of this cycle 1, 2, 3, 4, 5. So what is this cycle? If you see it as a function, what does it mean? F of 1 is 2, f of 2 is 3, f of 3 is 4, and f of 4 is 5, f of 5 is 1. Is that part clear? That's what it means as a function. Is that clear to everyone? Is this dictionary between a cycle and a function clear? Like, can I get some responses so that I know? Okay, there's one yes. Does anybody? Okay, let's say uh, anyone who has a doubt in this, can you just put your hands up? Okay. Okay, so let's redo this since some of you have a doubt. Okay, so moving from cycles to functions, I think there's a doubt here only. So let's look at that. Cycle, let's say cycle notation, cycle representation, and functions. Okay. So, see, basically a permutation is a function, right? So, what do you mean by a function? You have some numbers. Here the set was 1, 2, 3, 4, 5. And a function means to every element in this set, you're assigning some other element in the same set. So it's a function from S to S. So to 1, you have to assign some other element in S. But another condition is it is not just any function, but you're demanding it to be a bijection. Right? So it has to also, apart from being a function, it has to satisfy the condition that it is 1, 1 and onto. So let's say to 1 you assign the value 2. To 2 you assign the value 1. To 3 you cannot assign 1 or 2 because you want it to be a bijection. So let's say we assign 3. To 4 you assign the value 5. And to 5 you assign the value 4. Is this clear that what I have done is written a bijection function from S to S?
Yes, ma'am. It's clear.
Okay. So we want, instead of every time writing, f of 1 equal to 2, f of 2 equal to 1 and so on, we just want a easier way of looking at this. So you just see whatever picture I have drawn here, We're just converting this into the notation. That's it. So we're just writing. So this is our S. So whatever I have drawn here, 1 goes to 2, 2 goes to 1. So we're just writing it like this. So this is just an easier way of representing the function. This exactly means what I explained previously. F of 1 is 2, f of 2 is 1, f of 3 is 3, f of 4 is 5, and f of 5 is 4. Now, we
Ma'am, I
want
have
to
one
make...
question.
Yes,
Is
sir.
it necessary that the element of S must be a natural number?
We are actually taking any finite set. So if you take, let's say, a set of n numbers, you can just see it as natural numbers. Like eventually, when you see the definition of groups and all, you'll see that it doesn't matter whether you take natural numbers or we're just interested in the cardinality of the set. So for simplicity, we're just taking natural numbers.
Okay.
You can define permutations on any finite set. So you can take, let's say, S is something, A, B, C. So you can take all bijections from this set S to S also.
Okay. I mean, that means I can take any number which is 1 and on 2.
Yeah. You can take any
Any,
set and take all the
any
functions
set.
from any set, finite set for now. We're working with finite sets.
It is not
So
necessary
you
to
can,
take only, it is not necessary to take only a natural number like 1 to 5, 1, 2, 3, 4, 5, like that.
no, you can take it, but that's what I'm saying. Eventually, for the purpose that we'll be using this for, you'll see that it is kind of, it doesn't really matter. But yeah, you can take any finite set. See, if you take any finite set, suppose it has 5 elements, in a way you can see it as functions from the set of numbers from 1 to 5 to itself, right? Like
So this
some
is more focused on the cardinality than the elements of the set, right, ma'am?
yeah, that's what, like, essentially what we're interested is in the cardinality, but I'm not able to give you completely justify what I'm saying, because probably maybe after 1 or 2 weeks of the course you'll see a much more justification of what I'm trying to say.
Okay, so
Well,
the elements of the set cannot be minus, as in like in integers.
no, you can take any set. Take
Oh,
any set. Okay, for now let's just keep it like this. You can take any set and take finite set, and you take the set of
okay.
all bijections from it.
Okay,
Do
okay.
it.
Thank you, ma'am.
Okay, so going back to what we
So
were
I
trying
have
to...
seen only the natural number only. I have seen all the books of the permutation. I have seen only the natural number, like this 1, 1, 2, 3, 4, 5. I have not seen any integer, minus or a rational number.
Uh, yes, sir, that's what I'm saying. If you just wait for a
Yeah,
few weeks of the course,
that was also my doubt.
yeah, that's what I'm saying. If you just wait for a few weeks, you'll see why it is enough to take these numbers.
The natural. Okay, okay, ma'am.
What, like the mathematical object that we are interested in,
Hmm.
uh, you will eventually see that it doesn't matter. So just for simplicity, everybody takes 1 to n.
Okay.
Hmm.
Yeah. But the permutation defined this, so the elements of the domain and codomain is right. Yeah, that's correct. Okay. So coming back to what we were trying to do, so we are just denoting the function in this way, right? This just means f of 1 is 2, f of 2 is 1. Now we further want to simplify this. So that is what the cycle representation means. So what we're doing is we're even trying to make it even more simpler. See what is happening here. Okay, let me draw it here itself. You have 1 goes to 2, and then you look at where 2 goes to. 2 goes to 1. That is kind of like a cycle, right? So you have, I mean, it's the same thing that I'm drawing again. So we just denote this by 1, 2. So this just means the function which takes 1 to 2, and you can think of other elements as being fixed, or Okay, so if we want to write the other elements, 3 goes to 3. So that is this. Here 4 goes to 5 and 5 goes to 4. So we have 4, 5 and 5 to 4. So, so this is just a different way of denoting the function. It's nothing, we're not doing anything new. So let us try to rebuild. Okay, let's just forget what we have. Let's just take this abstractly and we're trying to see what is this function, right? We want to explicitly define this, which means we want to say, specify what is g of 1, what is g of 2, what is g of 3, what is g of 4, and what is g of 5. So, looking at just this cycle, how do you say it? So, you start from the rightmost side, you look at where 1 comes first. So, you go all the way here, 1 comes here, and you look at where the immediate next element to 1, which is 2. So, g of 1 is 2. And now you want to know g of 2. So you look at where 2 is appearing here and it is going to 1. See, the last element is the cycle is going to the very first element. That's what it means, right? So here we had 1 going to 2, 2 going to 1. So g of 2 is 1. And 3 is not, there is nothing else appearing in the cycle of 3, which means g of 3 is 3. So 4, the next element is 5, which means g of 4 is 5. And 5, it's the last element in this cycle, so it goes to the very first element, which is 4. Is this clear? How we move from a function as a function to this notation to the cycle and back to writing it as this 2 rows?
Yes, ma'am.
Okay. So once this is understood, now we'll go back to what we were trying to do here. So we have this cycle, right? We want to write this as product of 2 cycles, which means we want to write it as product of cycles of length 2. And what we claimed is that writing it like this. So you take the first element with the last one, that is a 2 cycle, and 1, 4, 1, 3, 1, 2, so on. We're claiming that this actually works, right? So all these colorful arrows are just checking that this as a function, whatever has been written here, and this as a function are actually the same. So if you've understood how to move from a cycle to writing down the function and how to take product of cycles, you just work it out, and that's exactly what we have done. So should I do the working out again? Okay,
Yes, ma'am, please.
okay, fine. So forget everything. Let's just verify that this cycle and this product of cycles that we have written is the same thing. Okay. So now our aim is to check that this 1, 2, 3, 4, 5 is equal to 1, 5, 1, 4, 1, 3, 1, 2. Let's give them names for simplicity. We'll call this F1, we'll call this F2, we'll call this F3. A more pleasing way maybe F4, F3, F2. Okay. So what is it that we want? When we say these two are equal, what do we mean? We have F1 on one side, which is a function from S to S. We have we have these functions f2, f3, f4, f5. So we have S to S, we have f5, we have S to S, which is f4, we have f to f, which is f3. So I'm individually seeing these as functions. Just this as f5, this as f4, and so on. So we have f2. So we know how to compose these functions. So you have f5 composite f4, composite f3, composite f2. So eventually what you'll get is a function from S to S. So what we're trying to say is that this function f1 and this function that we obtain by composing all these sequence of functions are in fact the same. This is what we're checking when we relook at it in terms of functions. Is this okay for everyone? So I will have to go a little beyond time to complete this. I hope that is okay with people.
Okay, ma'am.
Yeah, is this clear what we are doing?
Yes.
Okay. Any questions so far?
Yeah, madam. Can you explain this again, madam? Last how to convert this permutation into a function?
Convert what into function, sir?
Permutation into function. You said no. That f5, f3, f4, f3, f4, f2.
Like you want to know how to convert the
Yeah.
from cycle notation to function?
Yeah.
Okay. So, uh, so I'll just do this example again. So you can just look at it. See, you see this cycle 1, 2. What does it mean? What is the image of 1?
2.
2, right? So g of 1 is 2.
Yeah.
And what is the image of 2?
1. That I
Yeah,
got.
exactly. So similarly, you do it for the other things.
Yes. This I
So
got. But what you said last, no? That f5, f4, f3, f2. Yeah.
okay, so here what I'm trying to say is, see, what we're trying to do is verify that this cycle is same as product of these cycles, right?
Hmm.
So what do we mean by product of cycles and cycles? Each cycle we can see it as a permutation. It is you can see it as a function from S to S, right?
Mm-hmm.
So I'm calling this cycle as the function F1.
Okay.
So just this part, 1, 5, this can be seen as a permutation, as a function from S to S.
Mm-hmm.
So we are calling that function F5.
Okay.
And this function we are calling it F4. So when we say that we have to check that this cycle 1, 2, 3, 4, 5 equal to cycle 1, 5 into 1, 4 into 1, 3 into 1, 2, what it means to say in terms of functions is this composition is same as F1. That's all is what I said.
Okay. Got it.
Yeah.
Thank you.
So we'll just check it manually maybe. So okay, so let us write each F2, F3, F4 separately. So F2 is, okay, we'll start with F1. F1 is this cycle 1, 2, 3, 4, 5. So again, I think one thing that you should be thorough with is how do you move from one notation to another? How do you write it as a function? So this is basically, you look at 1. So as a function, what we mean is 1, you go to the cycle, see what is its image. When we say image in the cycle in notation, you're just seeing what is sitting to the right hand side of 1, which is 2. Now 2, you look at what is sitting to the right of 2, which is 3. 3, it is 4. 4 goes to 5. And 5, the last element in the cycle is pushed to the first one. So you can imagine it, literally as a cycle. 1, 2, 3, 4, 5 sitting like this. So 5 goes to 1. Now let's write out the other F2, F3 and so on. So our F2 was, oh sorry, I can start with just a cycle. So F2 was 1, 2. So what is this as a function? We have 1, 2, 3, 4, 5. So look at 1, 1 goes to 2. So 1, the image of 1 is 2. The image of 2 is 1. Now 3 doesn't appear. So if we look at, the previously what we have done. Yeah, if you look at this, what we said is if there is cycle of length 1, we can just ignore them. We don't write it in the notation. So what it means is there is no 3 appearing here, which means 3 is coming as a cycle of length 1, which means in terms of function 3 is going to 3, 4 is going to 4, 5 is going to 5. So put it in simple words, whatever doesn't occur in this cycle notation, it is being mapped to itself. Is this okay? How we converted F2 into a function, like moving from cycle notation to the function?
Yeah.
Okay.
Yes, ma'am.
So same thing we'll do for F3. So we have 1, 2, 3, 4, 5. I'll be a little fast now. So 1 goes to 3, 3 goes to 1. Rest are all not appearing, so they go to themselves. So F4. Sorry. And F5. Okay. So when we go back here, what have we achieved? We have achieved the function F1, or at least we have understood what is the function F1, where are the elements going. We have understood F2, F3, F4 and F5, right? Now we just take the product and see that F1 is the same as F2 composition with F3, composition with F4 and composition with the F5. So what we want to calculate is, so let's just do one step, not even so many at a time. Let's do F3 into F2. See, what we want is F1 is equal to F5, F4, F3, F2. So let's just start with this, F3 into F2. So F3, F2. What is this? F3 is 1, 2, 3, 4, 5. 3, 2, 1, 4, 5. F2 is, so you can look at what F2 is. So now what is this? When you take the product, as we saw, you first look at the right side. So what we want to do is we want to know what is the product. So we want to know the image of 1 under the product. So you first look at the right side function. You see, you take 1, you look at the image of 1 under this F2. So where is it going? To 2. Now you look at 2 here and see where is it going. So finally what is happening? F2 is sending 1 to 2, F3 is sending 2 to 2. So you just follow this arrow, you're sending 1 to 2 eventually, right? So I'll do one more. So here 2 is going to 1. So you come here and see where 1 is going to, which is 3. So you have to follow the arrow all the way from this 2 to here to here. So 2 is going to 3. Is this clear how to take product?
Yes, yes.
Okay, so you can continue this process. Once you get F2, F3, sorry, F3 into F2, you take F4 and take product with it. And once you get this function, you take F5 again. So you'll see that this is equal to F1. So you can try this if you've understood the procedure. We are way beyond time. So are there any more questions?
Excuse me, ma'am.
Yeah.
How do we find this is the required product for us? Like, is it just a hit and trail method, or is there any general idea to find the two cycles?
You're saying this one. How did we guess that?
Ha, 1, 5, 1, 4, 1, 3, 1, 2. Ha, yes, ma'am. How did we guess it?
Okay. So as I said, one way is you just think through it. I said, like one of the thing I said, you just think about boxes and how would you exchange it to go here. You can literally try it with boxes and see. You have two hands. You try to exchange it to come here. You'll reach this. And this is not the only way. There are other ways to do it also. So you can try to come up with. This is not, the only way of writing a cycle as product of this. There are multiple ways. This is just one possible way. An easy way of looking at it.
Thank you so much, ma'am, for explaining this again.
Yeah, welcome. So one exercise or one thing, if you want to think about it, is try to come up with other ways of writing it as product of two cycles.
Okay.